this is about HOL. That's a language I kind of came up with, I don't know, maybe 10 years ago or something. But I never really worked it out until 2 years ago, Colin Rothgang, who was at the time doing his master's thesis with Christoph Benzmüller. He's doing a PhD in Madrid now. So he approached me, and his topic at the time was to do something with higher order theorem provers, maybe generalizing them a bit. I thought, hey, we could work out this HOL language I had been thinking about, and at the time I thought it would be a 1-week thing to get him started. And in some sense that was true, because he implemented it in basically 1 week, but then it took a year to actually prove the soundness and completeness theorem, which turned out to be a lot harder than I thought at the time. So I'm going to introduce that logic. We published it at Pate last year, and I'm going to transition gradually into current work where it gets more and more open and where I'm not sure which things are going to work, so I'm happy to receive questions and feedback in those sections. So let's start with the section that we've understood well, where we just add dependent types to HOL, and then we go do the subtyping later. And yeah, as Michael said, one motivation of this work is that we want to increase expressivity of automated theorem proving languages while staying close enough to automated theorem proving that we can actually still build ATPs for them. So we definitely do not want to have like a full dependent type theory with universal and everything, which is far too far away from ATPs, but just see, well, if we take HOL, can we just make it a little bit more dependently typed while still retaining automation? So to wake everybody up, let's start with a quick show of hands. Is this formula true or not? True? Not true? Not enough information? So if you ask people, most of them will say it's true. But then if you ask a type theorist, especially when working in dependent type theory, they might point out this special case to you. What if f is dependently typed? So from xa going to b of x, then f of x and f of y are going to have different types. And it's entirely unclear if this is even well typed in the first place.
It was true until 1985.
So the question then for language designers is, should we make this true, no matter the cost? Or do we have to work around this issue with the different types somehow?
Florian, you used the word true.
Yeah.
And then you suddenly changed it to true.
Okay, yeah, I mean, then it would be the same thing. Well, at this intuitive level, where we're basically asking the language user, the user will not care. But yeah, so from the language designer perspective, the right word would be provable. Should we change our axioms and roots in such a way that this becomes derivable? So there's two paths. One is you don't make it derivable, in which case typing is decidable and you more or less go towards the dependent type theories that are currently mostly in use, like Cork, Lean, Park. You typically have to work around the fact that these two types are not equal, maybe some kind of transfer functions that get you from one to the other, because everybody knows they're essentially the same, or so there's usually some kind of isomorphism or transfer. Maybe you come up with a language where you say, okay, this is a feature, actually, equality over here is like isomorphism. So some people would say that's a bug, some like it. Or you can introduce two kinds of equalities, one that stays decidable, one that's undecidable, and you get like the propositional versus definitional equality split. And the other alternative is you just say, no, this has to be equal, and I'll make it equal no matter what happens. So you get a pretty simple language from a user perspective, but you get a very complicated type system now because, as we will see in a moment, then typing becomes undecidable, because you could have arbitrary axioms that about this equality here. So then arbitrary axioms and assumptions leak into your equality of types. Since the equality of types is needed for type checking, you have arbitrary undecidable axioms poisoning your type checking algorithm. So this talk is about this approach. Keep one equality and just use axiomatics equality everywhere. type checking becomes undecidable, and we see what happens. So how bad is it if typing is undecidable? It's typically a big problem. Systems that have been built on top of decidable typing usually are very difficult to retrofit, basically impossible to quickly adapt existing technologies. One of the major selling points we have when we sell like formulation and type series to practitioners goes away. But there are very successful examples where this is done. So we have major proof assistants who for a long time have been happily doing this. And in particular, HOL is very close to PVS, I think. And arguably that for mathematics is doing it also. Like equality is undecidable in math. Types are, well, either sets or predicates, but whichever one you pick, the equality there is also undecidable. So if we want to model mathematics, it might be reasonable to just use undecidable typing. And so then the idea to work this out, even though we were scared of it, was to say that, well, ATPs are getting a lot better. Like, first-order ATPs are now somewhat routinely handling higher-order logic problems, like Vampire has a very good higher logic mode. So maybe we can just keep pushing ATPs. Hey, you've been handling higher-order logic for some 10 years now. Here's another challenge for you. Make arithmetic theorem proving work for this slightly more general language. And of course, ultimately, we want to prove theorems anyway. That's undecidable. So maybe in practice, it doesn't matter that much if typing is undecidable. So that's, at this point, still a hypothesis, because the language is very young. We haven't really scaled it up yet. But basically, this is an experiment to see if it will scale. So let's see about the design of the language. This is simple type theory. So we have theories in which we declare base types A and typed constant C. And then we have context in which we declare typed variables. So very simple setting, no universals, no polymorphism, no type operators, just base types and typed constants, and then we can quantify over variables. Types, as usual, base types and function types, and then constants, variables, lambda abstraction and application. Now we go to higher order logic, which basically arises by adding the booleans and equality. So among the types, we add a base type of booleans, and among the terms, we add the base connective for type equality. And now we know, since Andrew's work, that with this, we can already define all the other connectives. So that's why we only need this as a primitive, but we get quantification, conjunction, and all the other connectives by definition now. Now, because we have booleans, we have to adjust our theories. We can now declare axioms. So I'm just writing a formula in the theory. So this is an axiom declaration asserting F. And we can also make local assumptions. So in our contexts, we can now assume a formula F. And now the idea of HOL is do the exact same construction.
I'm sorry, this is confusing. Is this the same F on both sides?
This and this? Or?
Yeah.
Yeah, it's this one. It's this arbitrary term, which has to be of type bool to count as an axiom. Maybe I should have put a keyword axiom in front here.
It has nothing to do with falsehood or as a boolean.
With what?
With falsehood as a boolean.
Oh, no. This is a non-terminal here.
What are better values?
So the idea of HOL is do the exact same construction, but start with pi types here instead of normal simple function types. So what do we have to change? Now our base type symbols have to be able to take arguments. So I'm writing a context, an arbitrary list of indexes or parameters for our type symbols. And consequently, when I'm using the type symbols as types, I have to supply these arguments, all of which will be terms. So we don't apply types, there's no polymorphism at this stage. We're currently working on polymorphism, but at this stage, we're only applying type symbols to terms. And then we change the simple function types to pi types. And everything else can stay the same. Again, based on the equality, we define all the other connectives, and all the rules of higher logic are just adjusted slightly to basically whenever we used to have arrow, now we have pies.
So the gamma and the dependent typing is a very simple gamma. You don't have a formula in it.
You could. I don't, but you could. It wouldn't change anything. Yeah, maybe I got the grammar wrong slightly because I'm technically allowing formulas here. That's what you mean, right? Yeah, so we're not doing that, but I think it wouldn't matter. So I'm repeating the grammar from before just for reference. Let's look at the rules a little bit. This is a normal rule to introduce equality, so you have two terms of the same type, and then the equality between them adds that type as type bool. And now we have the congruence rule for type formation. This is where everything, depending on who you ask, is fixed or broken. So you want to think about the type A applied to some arguments versus the same type A applied to some other arguments. When are these two equal as types? And here we just say, well, if all the arguments are equal, then the types are equal. The straightforward congruence that you would expect as a naive user, probably also expect as a mathematician. But of course, since this equality of terms here now depends on the context where we may have arbitrary assumptions, this equality judgment here is undecidable. It's as hard as proving theorems, and therefore equality of types is now undecidable. And this is the equality of types that we're using during type checking, so everything else becomes undecidable as well. From an inference system perspective, this is extremely simple and intuitive. And if you ask a naive outside user, they would never even notice that there could be a problem with this. But of course, if you ask an implementer, then this is a major problem down the road.
Right?
Yeah.
You haven't done anything interesting in the dependency.
What do you mean?
What is it? What depends on?
Sorry, I can't get the question.
Nothing in your type expression seems to have any interesting user dependency.
You mean this?
Yeah. You just have an application, that's it.
Yeah, and the X can occur here.
So only atomic types are dependent?
Yeah, and the pi types as usual.
Yeah, so there's nothing interesting going on here.
Well, what do you mean by interesting?
It's not governing anything. It's not governing a predicate, it's not governing the structure.
So I will introduce refinements and quotients later. Would you find that more interesting?
So nothing interesting.
I think you need types with a variable in them to do stuff.
Types with type variables in them or with term variables?
No variables. Individual variables.
Individual variable.
Pi types and sigma types.
But I have them. This is a pi type.
Go on.
Okay. Yeah, you could add sigma types as well. We didn't, but it wouldn't be an issue. Yeah, so what becomes problematic now? The first thing that is problematic is if you look at the context here. Now, these types A can contain terms and variables via these productions. So we have to type check those terms, which means whether or not this A is a well-formed type is now also undecidable. And it depends in particular on previously made assumptions. So these two productions here, where we declare new type variables and new local assumptions, they have to be able to alternate. So our context cannot be stratified anymore into a list of variable declarations and a list of assumptions. That's a key simplification that's usually done when implementing higher order logic. You can think then of just a set of variables and a set of local assumptions. That doesn't work anymore. We have a single list in which local variables and assumptions can alternate. And the same in the theories where axioms and type declarations and constant declarations can alternate. Implementation-wise, that's maybe not so bad, because there we already have lists of declarations in our input files. But in the calculi and in the algorithms, we typically employ this optimization and high-order logic that we can think about, that you can reorder this stuff arbitrarily. We're losing this ability now, so data structures for implementations usually have to change a lot. And it's a big problem for theorem provers that need to synthesize witnesses, because now, since the well-formedness of the terms you're synthesizing depends on the assumptions you've made, you can't just have a big hash set of synthesized terms anymore. You need to track very carefully which of your synthesized terms is well-formed under which assumptions. And the other thing that's a problem, that's if you look at implication. So if you remember the motivating formula I started with, so we would normally check this, being an implication, by checking that this is a Boolean and that this is a Boolean. But now we can't do it that easily because this is only going to be a Boolean under the assumption that this is true. Because if x and y aren't equal, then these two terms don't have the same type to begin with, so the equality is not well formed. So we have to tweak our well-formedness rule for implication to look like this. F is a normal Boolean, but then when we're checking the right-hand side of the implication, we're already assuming the left-hand side is true. So that kind of corresponds to the short circuit evaluation that we know from programming languages, where after progressing over the left argument of your binary connective, you can just assume its truth value in the second one. Similarly for conjunction, and depending on how you like classical logic, you may also do this for disjunction. So this is probably not that problematic implementation-wise, except we have to change the way we think about our binary connectives and how we implement them. But it has one major conceptual consequence, namely that the binary connectives can now no longer be defined in terms of just equality. So we need to make one of these dependent binary connectives primitive. And if we have one of them primitive, we can define the other primitive dependent, the other dependent binary connectives. And with that, we can finally make this formula check by concatenating the rules I've shown you.
Florian?
Yeah.
For conjunction, do you have two different introduction rules, or do you make conjunction not non-symmetric?
It's not symmetric anymore, yeah. So you lose a couple of properties. If you leverage the dependency, then conjunction is no longer commutative. And same for all the others. Okay, so this works. Now to the implementation. So the first implementation Colin and I did together with Krista, when we built it on top of Leo, is that we translate D-hole to high-order logic by erasing the dependencies. That is a standard translation technique. It's been well known for decades. So basically, whenever you have a dependent type, symbol applied to arguments, you drop the arguments, and all your pi types become function types. So then you're losing all the dependency information, but you recover that with a partial equivalence relation semantics. If you haven't heard of that, I'm happy to talk about it, but I didn't plan on talking about it because it's a bit incidental. Suffice to say that with this pair semantics in the translation to higher logic, basically for every D-hole type, we're introducing a binary relation on the whole side, which exactly captures equality and well-typedness. And then we can prove soundness and completeness of this translation here. And that's the part that took Colin 1 year. That's surprising because this dependency erasure is a well-known technique, but it turns out when you have classical Booleans around and you want to map the classical booleans of D-hole to the classical booleans of hole, then the standard dependency eraser translation is suddenly a lot harder. But yeah, if anybody has ideas for proving the completeness, I'm very happy to talk about it, because currently the proof is some 30 to 40 pages, and it's really painful, especially when we extend the language, and every time Colin has to extend this humongous proof to handle the new features. And then this year, there's work by Niederhauser, Brown, and Kalishik. Our involvement, I'm very happy that this language was picked up so quickly. And they actually built a native D-hole theme improver based on Tableau root in its name. It's still struggling with being perfectly complete because of this term synthesizing problem, but they're able to make it work quite well in practice. Okay, now for the second part, adding subtyping. That's where it gets more vague, because we're in the process of doing that. The basic motivation is, if you want to build D-hole, you have to pay a very high price to make typing undecidable. So once you've paid that price, you may as well double down on it and look at other type constructions that usually introduce undecidable typing. The two most prominent examples are refinement types, where you have a type A defined by a predicate, meaning the subtype of A containing all the elements satisfying P, and the quotient type, where you have the quotient of A by the equivalence relation R. So both of these have the feature that terms now occur inside types. Since those terms are subject to arbitrary axiomatic equality, these types naturally introduce undecidability. But the relative price from D-hole to introducing these is actually very cheap. So we basically get these for free. Changing the implementation is trivial, changing the translation is trivial. And of course, Colin has to spend a couple months adjusting the proof. That's the price to pay. If we had a simpler completeness proof, then it would be totally cheap. So, refinement types. So the grammar stays almost the same. We just add this one production for refinement types. I've just given you a hint of the rules to fortify your intuition. So if we have this predicate on A, and S is of type A, and we can prove P of S, then S is also in the refinement type. And now we have a subtyping relation like this. So here the language becomes even more like PVS, because this is pretty much exactly how PVS is built. Similarly for quotients, so first of all, in case you have never thought about that, you should understand that quotients and refinements are dual constructions. The intuition to keep in mind is that if you have a refinement, you have a canonical injection from the refinement into your base type. And if you have a quotient, you have a canonical projection from your base type into the quotient. So this canonical injection is usually a no-op in implementation, because we're reusing the elements of A as representatives of the elements of this subtype. Now for the quotients, the duality sometimes breaks down a bit. Depending on how you do quotients, you may want to use the equivalence classes as the elements of this quotient, rather than the original elements of A. So the idea we had here is we wanted to fully leverage the duality and really also make this a no-op. So the idea is we are reusing the elements of A as the elements of the quotient without any term constructor applied, which of course then means we have to change equality. Elements that were different at this type might become equal at this type. So we are interpreting equality now to say that the type A here actually tells us which equivalence relation to use to compare S and T. So equality of two terms is not an absolute property anymore. Whether or not two terms are equal depends on the type that's looking at them. So then the rules look something like that. So we have the production for the quotient here. If we have a term of type A, it's just immediately a term of the quotient. So the canonical projection is the identity. And subtyping-wise, the quotient becomes a supertype of the original type. That's a bit counterintuitive. So to understand this, you have to keep in mind that this kind of subtyping here doesn't necessarily make types bigger anymore. So the supertype can cardinality-wise also be smaller than the subtype. So the subtyping relation, it captures that we have a canonical no-op map from here to here. And we use the usual well-definedness conditions when we go out of the quotient. So the rules are, you have a question?
Yeah. So I guess this means that the equality, like you're really going to have to write the sub A divide R notation on the equality, because you could write subscript A instead, and that would still be.
That would be wrong, yeah, would be the wrong notion, yeah. So I'm still struggling with how I make the type checker infer the type argument. So I'm thinking it should be done something like how George always does it in Cork, that you somehow guess from the context which equality should be used, or which type should be used, Maybe the user can declare the canonical equality so that you don't always have to write the type subscript, but for now you have to always write it. So you get a subtype hierarchy then that looks something like this. So in the middle we have the base type, and we have the refinement by the trivial predicate and the quotient by the trivial quotient. So this is the equivalent closure of this is the diagonal, which then gives us the type A again. And these type equalities are on-the-nose equalities, not isomorphisms. And then in the two directions, you get here the normal refinements down to the empty type, which is an initial with the predicate that's false everywhere, and we have the quotient where everything is equal that gives us a singleton type, which is then terminal. But formally, we have subtyping going all the way up in the direction.
What makes these equalities on the nose? Or is that just an addition?
The rules, because we're reusing the elements of A as elements of the quotients and of the refinements. And if you define equality as having subtyping both directions and subtyping as having canonical no-op maps, then they just become equal. So we can characterize subtyping like this. So A is a subtype of B if and only if, whenever we have something of type A, it's also of type B. So we have canonical no-op maps between the types. Turns out that's equivalent to preserving equality. So if we have two elements and they're equal at type A, then they must also be equal at type B. So subtyping preserves typehood and equality. So as you go to the supertype, more stuff could become equal, but you never distinguish stuff that was already equal as a subtype. And now this is nice because this is a formula, so we can abstract away, and then we have this formula, which is equivalent to the subtype property. And now at this point, a very interesting subtlety appears. Originally, we thought we could just throw this formula into a theorem prover to handle the subtyping efficiently. Turns out this formula has a problem. This formula is, like if A, now this formula is a theorem if and only if it is well formed. Because for well formedness, you need to know that this is well formed, which you, in this context, only know if you've already proved this formula. So unfortunately, the soundness completeness theorem only works for well-formed formulas. So we cannot take a potentially ill-formed formula, throw it into the ATP. We have to first prove it to be well-formed, but that is then equivalent, is as hard as proving it in the first place. So we cannot, unfortunately, turn this formula into the ATP to prove subtyping. So instead, what we're currently working on is a subtyping algorithm to reduce subtyping to a series of theoremhood assumptions, which we can then send to the ATP. So as I said, the translation generalizes easily. Colin has generalized the proof. We, in principle, can do the type checker as before, but now there's proof obligations for subtyping in the type checking algorithm. And for that, we have to somehow answer these judgments by reducing it to judgments like this for Fs that we know to be well-formed, so that we can use the ATP to discharge them, and then we would have a subtyping algorithm relative to an oracle for this, for which we can use the field ruler. Yeah, I'm almost at the end. That works out perfectly. I think this is my last slide where I'm showing you the technicalities we're currently stuck on. So since we have to somehow figure out how to handle subtyping, we were trying to normalize types so that we can then have like a small, simple language of types for which we have to do subtyping. So it turns out, so we looked at the interactions between the pi type, the refinement, and the quotient. There's basically 4 ways how they can interact. You can refine the codomain, you can refine the domain, you quotient the domain, or you quotient the codomain. And then if you refine the codomain, you can reduce that to a refinement of the entire pi type. That's good, so you can push refinement and quotient to the outside. Our goal was to eventually have a normalization where we have plain d-HOL types, like just pi types, and one big refinement and one big quotient at the top. So this rule was pushing a refinement of the codomain to the outside. This equality you can use to push a quotient in the domain to the outside. But then for the other 2 cases, we couldn't prove equality. We could only prove subtyping one way. So refinement of the domain and quotient of the codomain, we could not push them up. So for a refined domain, this was the most surprising case. We could actually find counterexamples. So this one is not equal to this one. And the reason is simply that here, the b of x, the well-formedness of b might already assume that p is true. So in that case, this type isn't even well-formed. So you can't even start trying to make them equal. So that was the roadblock we hit that we haven't really worked around yet, that we can't push refinements of the domain out of the pi. And so this one, as far as we could tell, the other direction is independent of the axioms, but it seems to be consistent. So we just adopted that as an axiom to make these 2 equal. It certainly works for the soundness completeness proof. And so then eventually we're stuck with a normal form for types where we have pi types with possibly refined domains, and then arbitrary nesting of those. And at the very top level, one big refinement and one big quotient. And for this normalized form of type, we're currently trying to find the right criteria to handle subtyping. And if you have any ideas there, I'm very happy to hear them. So, thank you.